In this video, we're now going to be looking at the limiting sum, which is a unique property that appears in specific types of geometric sequences. Now, to really explore what this topic is, let's look at this sequence that I have here. We can see that it is indeed a geometric progression because every time we go from one term to the next, we're halving it or we're timesing it by a half. Now the question here says, what will be the sum of the infinite series below? Now when we have an infinite series, it just means imagine I have an infinite number of terms in this sequence. If I wanted to add up all these infinite number of terms, what do you think it will add to become? Now let's think about this, okay? When my teachers back in high school would introduce this topic, I thought it was pretty obvious that it would be infinity, right? Because you have an infinite number of terms. How can you add an infinite number of terms and they don't add up to infinity? Well, if you look at these values though, you can see that over time they're getting smaller and smaller and smaller. In fact, they're halving the value of the previous. Okay, now I'm going to tell you right now that it doesn't add up to infinity. And I'll show you, using this visual proof, what it actually will add up to. So, let's say the first term in the sequence that I want to add up is going to be 2. So let's draw up what will represent 2. I'm just going to say it's this rectangle over here. So that's 2. Now, the next term in that same sequence is 1. So if I want to add up 1 as well, I'm just going to draw in a rectangle that is half the size of 2. Okay, that's 1. Now the next term is half of 1, which is a half. And then we want half of half, which is a quarter. And then half of a quarter is 1/8. And then 1/16. And then 1/32. And then we keep halving and halving and halving. And halving and halving and halving and halving and halving. And you know what? If my pen or my iPad had the ability to zoom even more and more and more, I could just keep going. But the thing that I create is just always going to be so small. Now, eventually, if I have an infinite number of these terms, honestly, the box that I'm drawing is going to be so small, it's basically like I'm adding nothing over time. So we can say that even if I add an infinite number of terms in the sequence, it will add up to what we call a limiting sum, which in this case would just be equal to 4, because we have 2 over here, and then this thing next to it is essentially 2, it's just broken up. So that's pretty mind-blowing, isn't it? The fact that you're adding up an infinite number of terms, but it just adds up to 4. So that concept there is what the limiting sum is. Now, it's important to note that limiting sums only occur for geometric progressions, because when you have a geometric progression, you're just making the number smaller and smaller every time. All right, so, but it's like moving towards 0, I should say, because if you have like an AP, if you minus it, you're going to keep minusing it, but it's going to become like negative infinity, which is not a limiting sum. So we can say the limiting sum formula is given by this one over here. I quite think this is a cute formula because it has a little infinity sign in it. So we say S of infinity, so we're placing the n with infinity. That's because we're taking infinite number of terms. This is going to be equal to fraction a on 1 minus r. So all you need is your first term and your common ratio in order to find the limiting sum. The reason why is because n is implied to be infinity. Now, we can say that you can only have a limiting sum, or a limiting sum only exists if the absolute value of r is less than 1. Now, another way of saying this, that the absolute value of r is less than 1, is that r is between -1 and 1. I generally use this definition when I'm like solving some problems, because sometimes it requires you to bring it up, and you'll see why in a second. All right, so let's go ahead and answer some problems. Example 1, identify the common ratio and determine if a limiting sum exists. Okay, so first of all, before I even find the ratio, does this sequence look like it has a limiting sum? Now, the way that you tell is if the sequence goes smaller and smaller and smaller towards 0, that is when you know it has a limiting sum. If you look here, the numbers are getting larger and larger and larger. if I have an infinite number of these, they are definitely going to add up and give me infinity. So in this case, I'm going to say no, it does not have a limiting sum. But mathematically, if you want to say why it doesn't have a limiting sum, you have to identify its common ratio. So r is equal to 4. But I'm going to say since r is greater than 1, there is no limiting sum. Great. Next, B. Now, does it look like it has a limiting sum? Yes, it does, right? It goes smaller and smaller. So we're going to say that r is equal to, well, we go from 10 to 5, so we're halving it, and it's going to be negative a half. So I'm going to say since r is less, or since r is between negative 1 and 1, there is a limiting sum. Okay. And next, C, you can say, yes, it does, because going smaller, and the ratio in this case is 1 on 10. You can see that we're chopping off 1 0 every time. So we're dividing it by 10 or timesing it by 1/10. And I'm just going to say, since r is between negative 1 and 1, there is a limiting sum. Yay, that's it. Next, question 2. By evaluating S8 and S15 to the sum of the 8 terms, sum of the 15 terms, estimate the limiting sum for the sequence 9 plus 3 plus 1, correct to 3 decimal places. Okay, so without having to use the limiting sum formula, I can actually estimate what the limiting sum will be just by evaluating the sum of the first 8 terms and the sum of the first 15 terms, because they might actually converge to a particular value. So first of all, if I write down my sequence, I can see that A is equal to 9, R is equal to a third. If I find S8, we're going to use the geometric series formula. So that's when you know to use the geometric series formula. So you either use Sn or S infinity. You use Sn if they tell you how many terms to add up. If they explicitly say, find the sum of the first 10 terms, find the sum of the first 15 terms, then you use Sn. If the question implies that you're finding an infinite number of terms, or if it explicitly says find the limiting sum, that's when you know to use the limiting sum formula. So in this case, they said S8, S15, so we're going to plug it into Sn. So there's going to be A, well, let me write it down, A bracket r to the n minus 1 over r minus 1, or S8 equals to 9 bracket a third to the power of 8 minus 1 over a third minus 1. Okay, so it's going to be 13.497. Oh, I'm going to say 498 to 3 decimal places. Okay, and then now we're going to do the same thing for the first 15 terms added up. So we get 9 bracket a third to the power of 15 minus 1 over a third minus 1. So we get 13.499, which, to be honest, like if I were to round it up, it would be 13.500. So you can see here that even though there is quite a significant gap between S8 and S15 in terms of like, there's like a 7-term difference between them, you can see that they converge to what looks like a limiting sum of 13.5. Even if I had S of 200, you will find that it will be something along the lines of 13.499999999, etc. But it basically is 13.5. So I'm going to say that the limiting sum, it looks like it's going to approach 13.5. Okay, and this is without using the limiting sum formula. Okay, so what if you have the limiting sum formula or they want you to use it? Well, then this is what you can do. Find the limiting sum of each series, pretty straightforward. If we use it, we get the limiting sum formula looks like this. A is equal to 6 and R is a half because we're halving every time. This is going to give you 12. Okay, next, if I want to find the limiting sum formula of this one here, we're going to get A is equal to negative 2 on 3. Now, what's the common ratio? If you can't tell, just divide the second term divided by the first term. Negative 5 on 8. So we're going to get S of infinity equals to A over 1 minus R. Remember that there's already a negative in the formula, so it becomes 1 minus 5 on 8. So this gives you negative 16 on 39. Example 4, a geometric series has a limiting sum of 40. So we know that the limiting sum is 40, so S of infinity is 40, and its first term is 5. Find the common ratio of the series. So you can see here that we can still plug this into the limiting sum formula, but we're just going to be rearranging it to find the only unknown, which is R. So let's write it down first. Okay, let's plug in what we know. The limiting sum is 40. Our first term is 5, and then R is unknown. Okay, so now we just need to rearrange this. I'm going to bring the 1 minus R over to the left. Okay, you could expand it, or I'm going to divide both sides by 40. That gives me 1 on 8. And then this will give me 1 on 8 minus 1, which is negative 7 on 8, or R equals to 7 on 8. Example 5. For what values of x does the series 3x plus 6x squared plus 12x cubed plus ... have a limiting sum? Now, in order for a geometric sequence to have a limiting sum, the only condition is that the ratio needs to be between -1 and 1. And don't just try to remember that, try to understand why that is because if you have a ratio that is less than 1, that's like a small fraction, or it's just some fraction. And if you keep timesing it by a fraction that's smaller than 1, it's just going to make the number smaller and smaller and smaller, which means that the sum will converge to a finite value. So in this case, I'm going to find an expression for the ratio. So the ratio in this case, can you guys see what it is? Okay, it looks like to go from one term to the next, we're timesing it by 2x. So our ratio is 2x. Now, in order for a limiting sum to exist, the ratio must be between -1 and 1. So I'm going to say, let R be between -1 and 1. So 2x is between -1 and 1. And then you're finding the value of x in which that's true. So if I make x the subject in this double inequality, I'm just going to divide everything by 2. You now get that x is between -1/2 and 1/2. And that is the values of x in which this will have a limiting sum. So whenever you see a problem and it asks you when does the limiting sum exist, the only property that should be coming to mind is this one, that the ratio is between -1 and 1. Okay. And then now part B says, hence find the limiting sum in terms of x. So we're just going to find the limiting sum if it exists, keeping it in terms of x, so it's not going to be a number. So our a value is 3x, and we have 1 minus r in our denominator, where our r is 2x, so it's 1 minus 2x. And that's it. That's our limiting sum. Okay, example 6. Find an expression for the limiting sum of each series, hence solve for x. So if I want to find the limiting sum, you can see here the way that this is written, it might seem a little bit confusing, but on the left-hand side, we have this infinite sequence. You can see that it goes on forever, ... And we're told that it does have a limiting sum. So you don't need to prove that the R value is between -1 and 1. And then once you find the limiting sum, our job is actually to solve for x, because they've told us that the limiting sum is equal to 2. So this here is the limiting sum. So what I'm going to do is I'm going to substitute all this stuff into the limiting sum formula. So you get S of infinity is equal to a is equal to x, and r is equal to x on 3. So you're going to get a over 1 minus r. And now we're going to let the limiting sum equal to the right-hand side, which is 2. So if we plug that in, we get x over 1 minus x on 3 equals to 2. And then I'm going to make x the subject. So if I expand this, expand it, times it over to the other side, we get x equals to 2 bracket 1 minus x on 3. Then I'm going to expand this, so we get 2 minus 2x on 3. And then now I'm going to bring the x's over to the same side, so we get x plus 2x on 3 equals to 2. If I combine these two, this will become 5x on 3 equals to 2. And then if we just make x the subject, we get 6 on 5. Okay, so this is the value of x that goes in this sequence in which the limiting sum is equal to 2. Okay, example 7. Find the limiting sums if they exist, rationalizing denominators if necessary. So honestly, we're not doing anything fancy. I'm just giving you guys more complex problems where it's not as straightforward as just plugging it directly into the formula. It might be a little bit trickier. So for part A, if I want to find the limiting sum, let's see if they exist first. So the common ratio is going to be given by doing the second term divided by the first term. So the root 3's cancel and we get negative a third. So yes, it does exist. So that is our R value and our first term is 12 root 3. So if I want to find the limiting sum, I'm going to go A over 1 minus R. That's going to give me A over 4 on 3. 12 divided by 4 on 3 is just 9. So that's actually just going to give you 9 root 3. All right, next one, part B. So let's first see if there is a limiting sum. So R is going to be given by doing second term divided by the first. Let me just plug 1 minus root 2 on the calculator. Okay, so if I put that in the calculator, it gives me negative 0.4, which does fit in the constraints to have a limiting sum. So that's fine. And our A value is just 1. So if we plug that into the limiting sum formula, we get A over 1 minus R, okay, which if we continue to expand the denominator, we're going to get 1 minus 1 plus root 2, where the 1's cancel and we just end up with 1 on root 2, okay, which is giving like exact value trig vibes, but that's not really, we don't really need that. So now we just need to rationalize the denominator. So to do so, we need to times top and bottom by root 2, because that makes it a rational value. So we end up with root 2 at the top and just 2 on the denominator. Yay, so that is our limiting sum.